Welcome. This is part 2 of our applied optimization section. We're going to jump in right to a few examples. So this example says that VitaPlus sells 1,000 packages of vitamins every month at a price of $12 per package. Suppose that market research indicates that for each $1 increase in price, the company will sell 10 less packages of vitamins in that month. At what price should VitaPlus sell their packages of vitamins to maximize their revenue? And what will the maximum revenue be? So let's consider how we'd go through this, considering the ideas of quantity and price. We know already that revenue, by definition, is the quantity times the price of that item, Q times P. So we just have to consider, well, based on these changes, what does quantity and price look like? So let's start with the quantity. So currently we are selling 1,000, and once we do the increase of $1, we could say that we would be selling 10 less. So one way we could say that is that Q, just jot this down, is currently 1,000, but it'll go down by 10 every time we have an increase in price. Maybe we call that the $1 markup. We'll call that M. So this is the number of $1 markups. We'll just use that as a variable, little m. So for every $1 markup, we should be going down by 10. So that would be 10 times the number of markups, so minus 10m. The price currently is sitting at $12. So P is going to be $12, and for every markup, we're going to go increasing by $1. So we could say that this is going to be 12 times the markup M. So we have a definition for quantity and price, depending on what the value of this markup is going to be. So we can say this is going to be the revenue is equal to the quantity times the price. And now we can consider multiplying this out, seeing what this revenue is in terms of markups. So go ahead and take a look at our multiplication process here. There's 4 products here, back to some algebra. So we'll have 1,012 give us 12,000 plus 1,000m minus 120m and then negative 10m squared. If we summarize this, we'll have that revenue is going to be 12,000 plus 880m minus 10m squared. And that'll take us to the revenue function in terms of markdowns. So now that we have a revenue function, now we can consider maximizing it. We know that we can maximize our function by taking its derivative, its rate of change, and setting that equal to 0. We want to know where the rate of change of this function is 0, which will be the maximum in this case, because again, we have kind of a downward facing parabola shape. So we'll have R prime is 880 minus 20 times m. So setting this equal to 0, we'll end up getting 20M equal to 880. Dividing by 20 will give us the number of markups that we need to apply, and that looks like to be 44 if we divide by 20. So that would be 44 markups, which would actually translate to a markup of, looks like $44, because each markup is worth 44, or each markup is worth $1. So what is that price that is overall price that's going to maximize our revenue? Well, the price currently was 12. And if I have 44 as my markup, little m is equal to 44. 44 plus 12 is going to be 56. So 56 is going to be my grand total price. And we got to go out and find the actual maximum revenue. So let's do that for a minute. Again, we're going to go back to the revenue function. So that's right here. And I'll have to find that as well. So take a moment to do that. The revenue here we can say is going to be 12,000 plus 880 times 56. Or actually, and this is based on markup, so be careful with this. The m here is still 44. So we're going to do 44 as the input minus 10 times 44 squared. So go ahead and take that, and I'll confirm this as well. If you were plugging this into your calculator, I believe we should get that the revenue total is going to be $31,360 for that. Again, be careful there with going back to the revenue function, because we want to know the revenue is in terms of markups, not the actual price. So be careful to input just 44 instead of 56 in this case. So there's our total revenue. The next one involves, again, price and quantity, and we're going to consider how they can be related in a linear fashion. So suppose that the relationship between price and quantity of widgets sold is linear. When the price is $23, we can sell 4,783 widgets in a month. If we raise the price to $27, we can only sell 4,295 widgets in a month. We want to find the price that maximizes monthly revenue. Okay, so we have somewhat kind of two data points, and that's really how we want to apply these. Is really there's kind of two data points, two prices and two results in terms of selling quantity that we can consider. And again, we're telling ourselves that this, or at least it's been shown that this is going to be a linear relationship between these two data values. So in other words, I'm going to consider these as 2 points on a linear function, where we have price as the input, quantity as the output. Again, we're changing the price, so that's going to be the input into this expression. And then quantity would be the result. So it's going to be a P comma Q point that we're going to work with. So with these P comma Q points, the first one we could say at $23, we have a result of 4,783. And then the second point we have is 27 has a result of 42.95. So two linear points, again, price, comma, quantity. So since they have a linear relationship, we want to find really the line that goes between these 2 points. So that's our first goal, is to actually find this linear relationship and define it. So first, I'm going to consider finding the slope between these 2 points. I'll call this value m, and we'll go ahead and find slope just with our normal algebraic methods. So this would be the change in our output divided by the change in our input. And we'll just make sure that these have the same order. So it's 27 minus 23. So with a change of $4 in our input, it looks like we'll have a change of, looks like negative $488 in the price, or in the quantity, excuse me. So $4 in change in the price will result in a decrease of 488 in the quantity. So this will give us a negative 122. Again, that's going to be in dollar or widgets per dollar. So the number of widgets will go down 122 widgets will be made or sold here for every dollar increase in price. So let me say that again, a little tongue-tied. So for every dollar increase in price, 122 less widgets will be sold. So there's our slope. If we continue with this, we can go ahead and write this now in a point slope form for the linear function, and then work with that. So we have that Q minus Q1, the first quantity we could use is 4,783 is equal to my slope, and then we'll have the price minus the first price, which is $23. So point slope form here. We'll go ahead and multiply this out. We'll have the Q minus 4783 equals, we'll have negative 122p plus 23 and 122 will give us 2806. And then adding 4,783 or 4,783 to both sides will give us that final result for the linear function. Q is equal to negative 122p, and then we'll have plus, looks like 7589. Okay, so that would be our linear function that gives us our relationship. So a good amount of work here so far, but we're not quite done. So we'll have to keep plugging away here at our goal. So let's go ahead and refocus here. We have the relationship between price and quantity found out. But now we got to know, well, what am I actually going to go find? I want to go find what, we want to find the price that maximizes revenue, monthly revenue in this case. So we still need a revenue function. And we know, based on previous examples here, revenue is price times quantity. So we're going to use those two values again, price times quantity, and work out our revenue. So let's go on the right side here. and say that revenue, again, is going to be the price times the quantity, which we know to be, well, P is the price, and then quantity we could represent in terms of price with that Q equation. So we can input 122, negative 122 P plus the intercept 7,589. So our revenue function, if we multiply this, ends up being negative 122 P squared, and then plus 7,589 times P. So we do have a revenue function here, and this is what we want to go ahead and maximize. So taking a derivative, we'll call that r prime, setting it at equal to 0 in the next step. So we have negative 44, excuse me, P plus 7,589. That'll give me my r prime. And now we just want to set this equal to 0 to solve the rest. So that would be setting equal to 0. And doing a little bit of solving here for P, we have 244 times P equal to 7,589. And dividing by 244, we're going to get a P, or a price. You'll have a little decimal here, but we can round this off to $31.10 again. This will be the price per widget when we divide that term. So if we divide 244, we'll come up with that value there. So this is, again, the price that will maximize that monthly revenue. So it looks like based on those data values, we should increase our price just a little bit to go ahead and maximize our actual revenue. Let's take a look at one more linear or linearly related problem. This will finish out this video. So we have a baseball team plays in a stadium that holds 54,000 spectators. With the price, our ticket price, at $9, the average attendance has been 21,000. When the price dropped to $6, the average attendance rose to 27,000. Assume that attendance is linearly related to ticket price. What ticket price will maximize revenue? Okay, so this has the basic flavor of the question that we applied in our last example. We have two items, or an item, in this case it's a ticket, that has some value that is changing over time. And the attendance in this case is the output from that change in price. So again, we still want a price and quantity here, and this quantity would just be really the attendance, but we still can use the variables P and Q here if we'd like. So I'm going to continue using the price as our input, quantity as our output, and again, when I do the price here, price of the ticket, and then Q, we can really say is really the attendance. As long as we have that in mind, that's all right. If you want to use A, that's totally fine, but we'll just use P and Q again. One thing that's kind of extra information that we don't necessarily need is this 54,000. It would be helpful to make sure that our maximum attendance doesn't go over this stadium capacity of 54,000. So we'll just maybe make sure that that stays below 54,000 when we're done. So let's go ahead and dive into our problem with these two data values. So the first point that's given to us is where we have it at a price point of $9 and we have an attendance of 21,000. And then we have a price point of $6, 27,000 fans. Now, these are pretty low prices, but you can see how this could apply to really any sporting event that has generated revenue from ticket sales. So let's go ahead and find the slope between these 2 points and then apply this to a linear function. So we have the slope m is the change in attendance divided by the change in our price. So we have a 6,000 person attendance increase for a decrease in $6 or $3, excuse me. So that slope ends up being negative 2,000. So for every dollar that we increase our price, the attendance decreases by 2,000. So this would be 2,000 really people per dollar. So for every dollar increase in the price of the ticket, 2,000 less people will attend. Okay, let's continue with the process. Putting this into a linear function, we have that quantity Q minus Q1, we'll use 21,000 equals our slope 2,000, negative 2,000, times price minus the first price is $9. Okay, and let's go ahead and continue with this. I'll put a little tail on my Q just to represent that as my Q instead of my 9. So that would be Q minus 21,000 equals negative 2,000 times P, and then plus 18,000. If we add 21,000, we can say that Q, the quantity, is negative 2,000 times P plus 39,000. So that will round out our linear function in terms of price. And in a similar fashion, we're again searching for maximizing the revenue. So let's go ahead and consider that revenue function. Revenue, again, is going to be the price times the quantity, so no change there. Price times quantity, and we know that the quantity is defined by that linear function. So just so that doesn't look like a function, this is times quantity. So we have P times the Q, which is going to be negative 2,000 times the price plus 39,000. We'll do a little bit of rearranging here, distributing that to negative 2,000 P squared plus 39,000 times the price. We'll go ahead and make sure that we have a derivative for that revenue function. So taking that power rule derivative, and setting that equal to 0 to find the maximizing, or the price that will maximize this revenue function. So setting equal to 0. We'll have 4,000p set equal to 39,000, and we'll finally go ahead and divide by 4,000. And it looks like we will get 39 over 4, which we could actually translate as a decimal because we're going to do a price here, and that would be 9.75 or 9 3/4. So this would be a price here. Again, that's the price of each per ticket. And that will, again, be the price that's going to maximize the revenue for this baseball team through the ticket revenue. All right, well, thank you for watching this video. We'll take a look at some more examples with optimization in the next video.